Hello everyone. Today we are going to learn about spiral similarity in geometry. So spiral similarity is a transformation of the plane that is done about a point called a spiral center. And it is a combination of rotation along with the dilation about the spiral center. So spiral center can be anywhere on the plane, and if you consider a point P, then it is the entire plane is rotated about point P and it is dilated, means it is expanded, or it can be contracted about the point P, and the final transformation is said to be spiral similarity. The order in which you perform this is immaterial because you will end up with the same transformation at last. So, for example, if you take a line segment BC and if you wish to rotate it first, then it goes to some other place B prime C prime, and then if you dilate it, maybe it increases its size and becomes XY. So this is a typical example of spiral similarity. Two triangles can also be spirally similar, and one of whose vertex is the spiral center and other two vertices are not the spiral center, of course. And when you rotate them, the angle at A and the other two angles are preserved, whereas the side ratios would be the same for all three, but actual side lengths increase or decrease. So, interesting question in this idea is that given two line segments, can I always find a spiral center that takes one line segment to the other? And let's try to answer it. So here we go with the diagram that we ask ourselves about the existence or the way to find the spiral center that takes the line segment BC to another line segment XY. So that means I have to find some point A on the plane such that when I rotate the entire plane about this point A, then I should get some triangle like this, say B prime C prime, and upon dilation, B prime should go to X and C prime should go to Y. Now this clearly means that triangle ABC is similar to triangle AXY because rotation and dilation preserves all three angles. So we end up getting that AB upon AX equals AC upon AY equals BC upon XY. So notice that we know the length of BC and XY. Thus we actually know this ratio. So K, which is equal to the ratio, is known to us. Thus AB by AX is a given ratio K. So the length AB upon AX is known, and we now have to think about the locus of points which have the same ratio of distances from the points B and X. So let me put the question in a better way. Given 2 points, over here it is B and X, what is the locus of points which have the same distance ratio from B and X? So let's call the points on the locus to be P. So, and let's call the distance ratio to be K. And I want you to think about the locus whose distance ratio from B and X equal to K. Turns out that it is a circle around. Turns out that it will be a circle whose diameter are the points lying on the line BX, say P and Q, such that they divide the line segment BX in the ratio K internally and externally. So that is BP by PX is equal to K and BQ by QX equals minus K. We use negative symbol to represent external division. And let's quickly see a reason why this is true. Supposing if you consider a point T on this circle, remember this circle has PQ as its diameter. That's how it is defined. And you can see that TTQ angle is 90 degrees. Now let's join TB and TX. Call angle BTP to be theta. Then angle BTQ would be 90 minus theta. And let angle XTP. Let angle XTP equal alpha. Let's do some manipulations here. So BP upon Px equals, we know that it is K, that's how it was defined. But we can equate them through area ratios. That is, half AB sin theta formula implies that it is half BT times TP times sin theta whole divided by half XT times TP times sin alpha. Thus we get it is equal to BT sin theta divided by XT sin alpha. Now by a similar procedure, we can see that BQ by QX equal to BT sin of 90 minus theta upon XT sin of 90 plus alpha, which equals BT cos theta by XT cos alpha. Notice that both of these ratios equal K, because that's how the points P and Q are defined, and thereby equating both of these equations, one would get sin theta by sin alpha equal to cos theta by cos alpha, implying tan theta equal to tan alpha. And since here the angles are less than 180, we can directly equate them, theta equals alpha. Thus we conclude that value of alpha equals theta, and thus going back to the diagram, we can see that TP is the angle bisector of BTX angle. TP is the angle bisector of angle BTX. So now one could conclude by the angle bisector theorem that BT upon TX. So now we can directly say that BT upon TX equals BP upon PX, BP upon PX. Thus it equals the value. So hence this circle is the locus of points that have the same distance ratio from the points B and X, which equals K here. So let us use this logic onto solving the question we proposed. So here is the problem, and spiral center has the property that BA upon AX equals K, as well as CA upon CY equals K. This is due to the fact that triangle ABC is similar to triangle AXY. So we can conclude that point A lies on the circle that defines the locus of the points with constant distance ratio, because we know the value of K. Hence the locus can be determined, and A lies somewhere. The point A lies somewhere on the circle. Similarly, one can construct such circle from CY, because CA upon CY is the same ratio K. So if one constructs such circle, clearly the intersection of these two circles would be the center of spiral similarity. And here is the diagram after construction. As you can see, the points E and H are the internal and external bisectors of the line segment BX such that the ratio is K. And the first circle, let's call it omega 1, is constructed with HE as its diameter, and the second circle, whose diameter is again the internal and external bisectors of CY with the same ratio K, and the circle meets at the point A, creating the center of spirals. One can as well take the second point of intersection, the spiral similarity, but even A could denote the center of spiral similarity. I hope you enjoyed the video. The link of document will be available in the description. You can as well comment your own ideas on this. We will meet in the next video. Happy learning. Bye.